Hi there, this is Miss Barber. We begin the next lesson, Limit Rules. We will now learn basic properties of limits and how to apply those rules to find limits. Motivating thought exercise. To graph the function y equals 2x plus 1, what should be your first step? Recognize that the function is linear and the graph is a line. To graph the function y equals x squared, what should be your first step? Recognize that the function is a quadratic and the graph is a parabola. If you do not recognize the function from the equation and the graph of that function, your next option is to make a table of values with sufficient number of ordered pairs and plot the points on an xy axis. As with graphing functions, the limit properties are useful only if you recognize the functions to which the properties apply. If you do not recognize the functions, then you still have the remaining options of building a table of values to determine function behavior as x approaches the desired limit value, or plotting sufficient number of points to sketch the graph. Properties of limits. Let lowercase a, lowercase k, uppercase a, and uppercase b represent real numbers, and f and g be functions such that the limit as x approaches a of f of x equals cap a, and the limit as x approaches a of g of x equals cap b. For limits that exist and are finite, we have the following limit properties. Name of property, the constant property. The property states that the limit as x goes to a of any constant is that constant. Remember, if you're looking at a constant, you're looking at, say, y equals 7. It's a horizontal line. The value does not change. The name of the property would be x, and so the limit as x approaches a of x equals a. X takes on whatever value that it's approaching. The constant times a function. The limit as x approaches a if the constant times the function f of x is equal to, the constant is pulled to the outside of the limit symbol, so k times the limit as x approaches a of f of x, which is just the constant k times the limit value cap a. Some difference of functions. The limit as x approaches a of the sum of the or difference of the functions f of x plus or minus g of x is equal to the sum of the two separate limits. That is, the limit as x equals a, or x approaches a, of f of x plus or minus the limit as x approaches a of g of x, which is just the sum of the limits a plus b, or it should actually say plus or minus. The product of functions. So now you're multiplying two functions together. The limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x, which is equal to the product of a times b. The quotient of functions. The limit as x approaches a of f of x over g of x is equal to, let's observe, the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which would be the ratio of a over b as long as b does not equal 0. Now, function raised to an exponent. The limit as x approaches a of f of x raised to the n is equal to, notice, the limit as x approaches a of f of x, all in parentheses, raised to the power of n, or more simply put, the limit of the inside function, which is a, raised to n, where n is a positive integer, and the limit as x approaches a of the nth root of f of x, we put the root symbol completely outside, or more simply put, we put the limit expression completely under the root. So we'll have the nth root of the quantity, the limit as x approaches a of f of x equals the nth root of a. Exercise 1.2.1. Use the properties to find limits asked for. Try to determine the property or properties used. Part A. The limit as x approaches 3 of 7. This one uses the constant property, and that property states that the limit as x approaches a of k equals k. So, to match up the parts, x is approaching a, in this instance it's 3, and 7 is a constant, so the limit is also 7. Let's look at part B. Find the limit as x approaches 11 of x. This one uses the property that says the limit as x approaches a of x equals a. So now the a that matches up with our problem is 11. The function is x, so the limit as x approaches 11 of x is 11. And finally, part C, the limit as x approaches 6 of 9x. We're going to use the constant times a function property, and so let's go through each of the steps. That property states that the limit as x approaches a of k of f of x is equal to k times the limit as x approaches a of f of x. So let's rewrite this, bringing the constant outside, times the limit as x approaches 6 of x. Continuing. Now we need to determine the limit itself, and so the 9 stays put, and we know how to find the limit of x approaches 6 of x. That's similar to part B, and so we'll multiply that by 6, and so the answer is 54. Let's continue. Part D. Find the limit as x approaches 2 of x to the 5th. Here we're going to use the exponent property, and so applying it, it starts with the limit as x approaches a of f of x to the k. We will identify the f of x as our function x and the power k as 5. Let's rewrite this using the property, so we will have in parentheses the limit as x approaches 2 of x, close the parentheses, and raise it to our power, which is 5. Now we compute the limit inside the parentheses, and that one is the identity. So as x approaches 2, the limit also approaches 2, and we do 2 to the 5th. And so if you compute that, it's 2, 4, 8, 16, and your answer is 32. And finally, part E. The limit as x approaches negative 27 of the cube root of x. So we're going to use the nth root formula. The formula states the limit as x approaches a of the kth root of f of x is, and so we bring or pull out all of the root and then put the limit property inside, so we would have the limit as x approaches negative 27 of x. We'll continue, and we will have the cube root of, and x is approaching the number negative 27, and the cube root of negative 27, when simplified, is just negative 3. Part F. We will continue with the properties. We have a difference and a sum, so we can write this using the limit properties as the limit as x approaches negative 1 of x squared minus the limit as x approaches negative 1 of x to the 5th plus the limit as x approaches negative 1 of 4. So we've got 3 separate limits to compute, and the exponent property informed us that we can just take the limit as x approaches negative 1 of x and square that. Similarly, for the next term, we can just take, so we do minus and the limit as x approaches negative 1 of x to the 5. And for the last one, it's a constant, and using the very first property, it doesn't matter what x approaches, it's just going to be a constant. Now let's continue. Taking the limit of the first term as x approaches -1, we will have -1 squared minus, as x approaches -1, we will have -1 to the 5th plus 4. Now we just have basic arithmetic to do. -1 squared is +1, minus a negative to an odd number is negative, plus 4. And so this limit will be 1 plus 1 plus 4, or 6. Let's do part G, and we want the limit as x approaches 0 of the expression 5x minus 6 divided by 3 minus 11x. For this rational expression, let's take the limit of the numerator and the limit of the denominator. So we would have the limit as x approaches 0, 5x minus 6, divided by the limit as x approaches 0 of 3 minus 11x. Let's take each of the individual limits of the numerator. So I'm going to skip a step and just go ahead and put the constant outside the limit symbol. So I'll have 5 times the limit as x approaches 0 of x minus the limit as x approaches 0 of 6, divided by the limit as x approaches 0 of 3, and then I'll go ahead and pull the constant out, so minus 11 times the limit as x approaches 0 of x. Let's proceed. We will have 5 times x goes to 0, so times 0, minus 6 is a constant, divided by, we have the limit as x approaches 0 of 3, which is 3, and for the last term, you have the constant 11 times the limit as x approaches 0 of 0, and so this simplifies to -6 divided by 3, or just -2. Exercise 1.2.2. Evaluate the following limits if the limit as x approaches -3 of f of x equals 5 and the limit as x approaches -3 of g of x equals -2. Part A. The limit as x approaches -3 of 4 times f of x. Let's use the constant times a function property for the limit and express this as 4 times the limit as x approaches -3 of f of x. In this statement of the problem, we are told that x approaches -3 of f of x is just the number 5, so this limit will be 4 times 5, or 20. Part B. The limit as x approaches 5 of f of x. Let's note that we're given values for f of x as x approaches -3. Don't have any other approach, so at this point, can't do. Cannot evaluate because we are not given sufficient information. Let's continue. We've got part C, and this is the limit as x approaches -3 of, and let's go ahead and treat this as the quantity 6 times gx minus 9 times f of x. Let's first separate this into a difference of two limits, so we can write this as the limit as x approaches -3 of 6 times gx minus the limit as x approaches -3 of 9 times f of x. Now let's apply the constant times a function property to each of the two separate limits. We'll write the 6 outside the limit symbol. Then we have the limit as x approaches -3 of g of x minus, we will also pull the 9 out front of the limit. So 9 times the limit as x approaches -3 of f of x. In the statement of the problem, we are given the limits for each of these. And for the limit as x approaches -3 of g of x, that limit is 2. So we have 6 times -2 minus 9. And the limit as x approaches -3 of f of x is 5. So now we have -12 minus 45. And that's arithmetic. So it'll be minus, let's see, 57. Okay, let's do this again for part D. The limit as x approaches -3 of the square root of f of x squared plus 10 times g of x minus 1. Let's apply the root property first. So we will now rewrite this as the square root of the limit as x approaches -3 of f of x squared plus, I'm going to go ahead and write the 10 on the outside of the limit symbols. That's the constant times a function. So 10 times the limit as x approaches -3 of g of x, and continuing minus the limit as x approaches -3 of the constant 1. Let's continue some more. We've got to do one more thing, and that's with the squared. So we will have the square root of the limit as x approaches -3 of f of x squared. Then we can have plus 10 times the limit as x approaches -3 of g of x is -2 minus the limit as x approaches -3 of a constant is that constant, so this will remain 1. We've got one more limit to compute and then some arithmetic. So the limit as x approaches -3 of f of x is, that's right, 5 squared minus 20 minus 1. I don't have a calculator, so I'm going to do each of the steps separately. So I'll have the square root 25 minus 20 minus 1. Okay, that I can do. So 25 minus 21, I want the square root of 4. And that answer is positive 2. Algebra refreshers. Definition. A polynomial function of degree n is a function which can be expressed in the form p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus x sub 1x plus a sub 1x plus a sub naught, where n is a non-negative integer and the leading coefficient is not 0. The numbers a sub 0, a sub 1, a sub 2, ... to a sub n are called the coefficients. The number a sub naught is the constant coefficient or constant term. The number a sub n, the coefficient of the highest power, is the leading coefficient, and the entire term a sub nx to the n is the leading term. Definition. A rational function is a function that can be written in the form, please excuse the double writing of function, is a function that could be written in the form r of x equals n of x to suggest numerator divided by d of x to suggest denominator, where both n of x and d of x are polynomials and the domain is the set of real numbers for which the denominator does not equal 0. Exercise 1.2.3. Determine which of the following are polynomial, rational, or neither. Let's look at A. 5x to the 7th minus 8x to the 4th plus 14x squared plus 6x plus 9. This expression is the essence of a polynomial function. All the powers are positive integers, and there are no negatives or square roots or anything like that, so that one is a polynomial. B, f of x equals 2 to the x plus 3x minus 7. Let's observe that 2 to the x is not a leading term polynomial expression. It is an exponent, and therefore b is neither a polynomial or a rational. C, g of x equals the quantity 4x minus 7 divided by the absolute value of 7 minus 4x. While this looks like a rational expression, the absolute value notation cannot be used and that expression still be a polynomial, so part C is also neither. And then let's look at D. H of x equals the quantity 19 plus 4x divided by the quantity x cubed minus 5x squared plus 2x minus 1. The numerator is a linear equation, which is a polynomial, and the denominator meets all the requirements of a polynomial also. So we have a ratio of polynomial over polynomial, which tells us it is a rational function. Now that we have reviewed polynomial and rational functions, let's study the limits of polynomial and rational functions. The limit as x approaches a of any polynomial is the value of the polynomial when x equals a. That is, if p of x is a polynomial, then the limit as x approaches a of p of x equals the polynomial evaluated at a. The limit as x approaches a of any rational function, simply put, is evaluated as the numerator at a divided by the denominator at a, as long as a is in the domain of the rational function. Exercise 1.2.4. Evaluate the following limits. Part A. The limit as x approaches negative 1 of x cubed minus 5x squared plus 6. The property we just learned tells us that in a polynomial function, we could just plug in the approaching limiting value. So with that property, we will compute this limit as negative 1 cubed minus 5 times negative 1 squared plus 6. Now we'll follow up with the arithmetic. Negative 1 cubed is just negative 1. Minus 5 times negative 1 squared is just 1. Plus 6. Going from the left to the right, negative 1 minus 5 is negative 6. Negative 6 plus 6 is 0. Let's continue to part B. The limit as x approaches 5 of the numerator x plus 2 divided by the denominator x squared minus 4. This is a rational function or rational expression. Numerator and denominator are both polynomials, so we essentially just evaluate at 5. So we will have 5 plus 2 divided by 5 squared minus 4. The numerator, 5 plus 2 is 7. The denominator is 25 minus 4, because 5 squared is 25. Let's simplify some more. 7 divided by 25 minus 4 is 21. Ooh, and that simplifies to 1/3. Let me call something to your attention in just a moment, and we'll follow up. If we just look at the expression x plus 2 of x squared minus 4, we can write the numerator as x plus 2, and the denominator is a difference of squares, so x plus 2, x minus 2. The common factors cancel, and we get 1 over x minus 2. We still have to remember that even though the values canceled, x still cannot be negative 2. And if we evaluate at 5, you get 1 over 5 minus 2, which is 1/3. This is just to remind you that algebra is consistent. Exercise 1.2.5, if f of x equals x plus 2 quantity divided by x squared minus 4, find each of the following. So f of negative 2, that's just function evaluation. We would write this as negative 2 plus 2 divided by negative 2 squared minus 4. So that's 0 over 0. 0 over 0 is not undefined. At this moment, we say that 0 over 0 is indeterminate. That means we can't tell, so we have to do something else. Now let's look at the limit as x approaches negative 2 of the function, and we actually already did this. If you take the limit as x approaches negative 2 of x plus 2 over x squared minus 4, we're still going to get 0 over 0, which is indeterminate. However, indeterminate also is a directive. It means do something else. So let's continue with this, and I'll have the limit as x approaches negative 2 of x plus 2 divided by x minus 2 times x plus 2. The common factor of x plus 2 in the numerator and in the denominator will cancel. So now we'll take the limit as x approaches negative 2, right? Yes, of 1 over, what was it? Oh, x minus 2. And that will actually give us 1 over negative 2 minus 2, or negative 1/4. Isn't that strange? The function's not defined at negative 2, but we do have a limit at negative 1/4. This might be something that you recall from previously, and this is a point discontinuity. Limit of a quotient with the limit as x approaches a of d of x, which is the denominator, equals 0. If the limit as x approaches a of n of x, which is the numerator, equals a limit value that's not equal to 0, and at the same time the limit as x approaches a of d of x, which is the denominator, and that equals 0, then the limit as x approaches a of n of x over d of x does not exist. Exercise 1.2.5. Evaluate the following limits. Part A, the limit as x approaches 0 of the quantity x squared minus 5x plus 6, all divided by the quantity x minus 3. We'll use the rational rule for rational functions here and just plug in. Let's see what happens. So if I put in 0 for x's, we get 0 squared minus 5 times 0 plus 6. And we divide that by 0 minus 3. So we got 0 minus 0 plus 6 divided by negative 3. That limit is negative 2. Let's do part B. I bet this one's not going to be as easy. The limit as x approaches 3 of x squared minus 5x plus 6 divided by the quantity x minus 3. So let's begin by plugging in. And we'll get 3 squared minus 5 times 3 plus 6 divided by 3 minus 3. So the numerator is 9 minus 15 plus 6 divided by 0. 9 minus 15 is, yep, that's right, negative 6 plus 6 divided by 0. Oh, we get the desired indeterminate form. That tells us we need to do something else. I'm going to suggest that we factor the numerator. So the limit as x approaches 3, we'll factor x squared minus 5x plus 6, and the two factors are x minus 2 times x minus 3 divided by x minus 3. So the x minus 3 in the denominator and the numerator cancel. And now we want the limit as x approaches 3 of the remaining numerator, which was x minus 2. So we will write this, plugging in the 3 for the x. 3 minus 2 equals 1. Exercise 1.2.6, evaluate the limit as x approaches negative 1 of x cubed plus 1 divided by the quantity x plus 1. It's a polynomial over a polynomial, so let's just plug it in. This would be negative 1, that's what the x is approaching, cubed plus 1 divided by negative 1 plus 1. So a negative raised to an odd power remains negative, and it also remains negative, so we've got 0 over 0. And that's indeterminate. If you've got 0 over 0, we say that it is indeterminate, and it's a directive to do some algebra. So let's factor the numerator. It's a cubic, so we'll write the limit as x approaches negative 1. We'll factor the x cubed plus 1. And so that's a sum of cubes. We can write this as x plus 1 times x squared minus x plus 1 divided by x plus 1. The x plus 1's are common to the numerator and the denominator, and now we can take the limit as x approaches negative 1 of the polynomial x squared minus x plus 1. The rule for how to find the limit of a polynomial allows us to just plug in the values. So if x approaches negative 1, we'll put in negative 1 squared minus negative 1 plus 1. Negative 1 squared is positive 1. Negative minus would give us a positive 1. And then we add one more. So the limit of this expression is 3. So let's formalize the term indeterminate. If the limit as x approaches a of n of x equals 0 and the limit as x approaches a of d of x equals 0, then the limit as x approaches a of n of x divided by d of x is said to be in indeterminate form. Note, we have worked examples in which indeterminate forms had limits. This is not always true. Each indeterminate form requires more research. Exercise 1.2.7. Find the limit as x approaches 2 of x minus 2, the quantity, divided by x minus 2 quantity squared. Let's plug in. This looks like a rational expression, so we could begin this just by plugging in values. Got 2 minus 2 divided by 2 minus 2 squared. 0 divided by 0 squared is still 0 over 0. This is indeterminate, and indeterminate means do something else. Well, we see a quick cancellation, but I'll expand it anyway. I'll write this as the limit as x goes to 2 of x minus 2 in the numerator divided by x minus 2 times x minus 2. That's what the squared means. So we can cancel one common factor in the denominator with the x minus 2 in the numerator. So now we will write this, the limit as x approaches 2 of 1 divided by x minus 2. That's still a rational function, so let's go ahead and evaluate. It'll be 1 over 2 minus 2, 1 over 0. If there is a non-zero number in the numerator and 0 in the denominator, we get to conclude that this limit does not exist because the 0 in the denominator term is undefined. Exercise 1.2.8. Use h of x below, so that's the piecewise defined function, to answer the following questions. The piecewise defined function, h of x equals x minus 5 if x is equal to or less than 3, and 2x plus 1 if x is strictly greater than 3. So let's attempt to answer these questions. A, what is h of 3? We want to evaluate the function at 3, and so we use the first piece because of the equal to or less than, and so this value we would compute as 5 minus 3, or 2. What is the limit as x approaches 1? Let's keep in mind that unless we are looking specifically at the cutoff points, and those are the 3, okay, everything else doesn't require much special work. So as x approaches 1, well, 1 is less than 3, so we use the first piece and then just plug it in. So this limit will be 5 minus 1, or 4. Now it gets a little bit tricky. See, what is the limit as x approaches 3 from the left of h of x? From the left means less than, and so we approach from less than. We are concerned with just the first piece, and remember, the limit has really nothing to do with what happens at that point, but what happens as we approach that point. Less than, or from the left of 3 means we use the first piece, so we will do 5 minus 3. That looks like the function value of 2. Now, what is the limit as x approaches 3 from the right? That means from numbers greater than 3, and that is the second piece of this piecewise function. So we will evaluate 2, put in 3 plus 1, so that's 6 plus 1, or 7. And finally, E, what is the limit as x approaches 3 of h of x? Let's observe that from the left and from the right, the limit values are not the same. So we say that this limit does not exist. Exercise 1.2.9. If f of x equals 7 minus x squared, find the limit as h approaches 0 of f of 1 plus h minus f of 1, all divided by h. Let's do this in 3 pieces. I would like to first evaluate f of 1 plus h. That merely means you take your f function, and every place that there is an x, so we have open parentheses squared, we fill it with the evaluating value. Now let's continue. We're going to have 7 minus, and if it's been a while since you've done algebra, remember a quantity squared means you multiply the 2 binomial terms together. Let's continue to simplify. So we'll get 7 minus, and I'm going to keep the big parentheses. Multiply this using the FOIL. So first terms together, it'd be 1 times 1. And then the product of the outside terms is h. The product of the inside terms is h. And when you add those, that's 2h. And finally, the last terms, h times h, is h squared. And let's clean this up one more time by distributing the negative. So you have 7 minus 1 minus 2h minus h squared. And I spoke too soon. We need to combine the 7 minus 1. So we get that f of 1 plus h is 6 minus 2h minus h squared. Now let's compute f of 1. That just means we evaluate the function at 1. So we'll do 7 minus, where the x is, we put in the 1 squared. So 7 minus 1 is just 6. Now let's put the pieces into the limit. So we'll have the limit as h approaches 0 of, and where we had f of 1 plus h, that expression we just found to be 6 minus 2h minus h squared, minus the function evaluated at 1, or f of 1, is actually the number 6, and all of this is divided by h. Let's continue. This will give us the limit as h approaches 0 of, the 6's cancel, so minus 2h minus h squared divided by h, and I think I see a common factor in the numerator, so let's factor out an h. That's the limit as h approaches 0 of, factoring out 1h, we get minus 2 minus 1 remaining h divided by h. Those h's cancel, and I'm out of space at the last moment, so let me go to a clean sheet. I need the limit as h goes to 0 of negative 2 minus h. So let me go ahead and say I need the limit as h goes to 0 of negative 2 minus h, and we can compute that. That would be negative 2 minus 0, which is just negative 2. The expression f of x plus h minus f of x all divided by h is called the difference quotient. It is a form of the slope formula. Practice simplifying the difference quotient. The notation is suggested the limit as h approaches 0 of the difference quotient, which is f of x plus h minus f of x all divided by h, is used in the definition of the derivative and is a very important part of this calculus course.